Swayam Prabha. Digital India. Educated India.
Hi everyone, this is Malika Pathak from Miranda House, University of Delhi. Continuing with the course on solid state for the students of BSc Honours Chemistry and BSc with Chemistry. This is Module 5 and Lecture 2 of the series. The academic expert of the course is Dr. Amrita T. Sheikh, and the recording is being done under the DTH Swayam Prabha project of the MHRD, New Delhi. Now, today in this lecture, we are going to take a look at the symmetry in the crystals. So, for that, we need to know the terms which are associated with the symmetry. So, for that, we are going to talk about the symmetry elements which are there: axis of symmetry, plane of symmetry, center of symmetry, roto-inversion. And then we are going to take a look at the crystallographic terms and the laws of symmetry. This will be followed by look at what are Wheeze and Miller indices, how are they calculated for any given plane, and how are they used in a crystal. We will also try and solve some numericals based on the Wheeze and Miller indices. So let's start with the lecture. Before we start with taking a look at the symmetry in the crystals, let's just recall what are the features of a crystal. We have already discussed them in the previous lecture, but let's just do a recall of that or recapitulation of that part. So the first thing is, what is a face, or what are the faces in a crystal? So those planar surfaces that you see in a crystal are called as the faces. So in a crystal, you will see there are many planar surfaces. All those planar surfaces are called as faces of the crystal. Then the line at which the two faces intersect. So if these are the two faces and the point, and this is the line at which they intersect, this is called as an edge. So an edge is the line at which the two adjacent faces intersect. Then comes the solid angle. So when you look at a crystal, you've looked at many crystals over the years, you realize that there are places where two, three or more edges intersect. So when three or more edges intersect, we get a solid angle. Now let's take a look at the interfacial angle. We have already done these in the previous lecture, but just for recapitulation. So what is an interfacial angle? It is the angle between the perpendicular to the two adjacent faces or the two intersecting faces. So let's say this is a face A and this is a face B. They both intersect like this. Now, so a perpendicular to a face A perpendicular to a face B, they will intersect at that point, and the angle between these perpendiculars is called as the interfacial angle. And you must remember that a crystal is bounded by three external elements: plane faces, straight edges, and interfacial angles. And they are related to each other by the equation F plus C is equal to E plus 2, where F is the number of faces, C is the number of interfacial angles, and E is the number of edges. So this angle is called as an interfacial angle. So interfacial angle is the angle between the perpendiculars or the normals of the two intersecting faces. Now let's start with the symmetry. Crystal symmetry or symmetry in a crystal. Now symmetry is a peculiar regularity which is observed in the arrangement of atoms, ions or molecules in a crystal. Now crystals can be classified according to their symmetry aspects. This could help us to understand the molecular properties such as dipole moment, optical activity, and spectral characteristics. Before we try and classify molecules on the basis of symmetry, we must first understand the terms symmetry elements and symmetry operation. Now, symmetry operation is the movement of an object which leaves the object looking the same. A symmetry operation brings the molecule into equivalent or identical configuration. So if I consider a cardboard which is shaped like an equilateral triangle, and if I rotate it at 120-degree angle repeatedly, I will get the same equilateral triangle. So that is said to have a symmetry. Symmetry elements in the crystal. A crystal may be symmetrical about a plane, an axis, or a center. That is, on rotating the crystal about the axis or reflection across the plane, the appearance of the crystal remains unchanged. The total number of planes, axes, and center of symmetries which are possessed by a crystal is termed as its elements of symmetry. To understand this, let us imagine a small two-dimensional crystal composed of atoms in an ordered internal arrangement as shown here. Although all the atoms in this lattice are the same, one of them is orange so that its position can be tracked. Now if I rotate the crystal by 90 degree, I notice that the lattice and crystal looks the same as what we had started with. Rotate it by another 90 degree and it again remains the same. Another 90 degree and it remains the same. Another 90 degree and we return to the original orientation. Thus, in one 360-degree rotation, the crystal has repeated itself or looks identical 4 times. We thus can say that the object has a fourfold rotational symmetry. Now look at the three elements of symmetry which are there in the crystal. One is the axis of symmetry, plane of symmetry, center of symmetry. Although we are also going to talk about the rotation reflection symmetry, the roto-inversion, but these are the three elements of symmetry which are there in the crystal. Now let's take a look at the axis of symmetry or the rotational symmetry. So what is the axis of symmetry? An axis of symmetry is the imaginary line which passes through the center of the crystal such that if the crystal is rotated about this line, it presents similar appearance more than once in one complete revolution through an angle of 360 degree. I am repeating, an axis of symmetry is the imaginary line which passes through the center of the crystal such that if the crystal is rotated about this line, it presents similar appearance more than once in one complete revolution, that is through an angle of 360 degree. Let's take a look at it. Now just see, this is a cube. Now if I rotate an object about an axis and it repeats itself every 90 degree of rotation, then it is said to have a fourfold rotation symmetry. The axis along which the rotation is performed is an element of symmetry. So just see, this is a cube. In this cube, through the center is passing a line. Now if I rotate this 90 degree, I get identical structure. Just see, just to understand whether we have rotated or not, we have labeled one of the faces. Not the face that is shown here, but the faces, the planar surfaces. So we've labeled one of the planar surfaces. Now if I rotate it by 90 degree, I get identical structure. Now in a 360 degree rotation, this has happened 4 times. See, one rotation I get same, another rotation I get same, another rotation I get same. So in a 360 degree rotation, if I get it 4 times, then it is said to have fourfold rotational symmetry. And the axis along which this has taken place is called as rotation axis. Now, this can happen as a twofold symmetry, threefold symmetry. So let's see what is a twofold symmetry. Now, if a similar appearance occurs twice in one revolution, that is every 180 degree, then it is said to have a twofold axis of symmetry or dyads. So if I imagine a filled oval, then it will have a one revolution after 180 degree, which will give you another and then another. So it has a twofold axis of symmetry. In the same way, if similar appearance occurs 3 times in one revolution, that is after every 120 degree. The axis is called threefold axis of symmetry. Just imagine I gave you an example of an equilateral triangle. If this is an equilateral triangle, I give it a 120-degree rotation, I get the same equilateral triangle. Another 120-degree rotation, I get the same equilateral triangle. So that is said to have a threefold axis of symmetry. See, just imagine this is a equilateral triangle. I give it a 120-degree rotation, I get the same. I'll give another 120-degree rotation, I get the same. Now, if the similar appearance occurs 4 times in one revolution, as in the previous case, that is every 90 degree, the axis is called fourfold axis of symmetry or tetrads. So dyads, triads, tetrads. So if I talk about a square that we had taken example, it is said to have a fourfold axis of symmetry. If similar appearance occurs 6 times in one revolution, as in hexagon, so just imagine a hexagon or a benzene ring or a hexagon, you will get the same identical structure if I give it a 60-degree rotation. Or in a one revolution of 360 degree, I will get 6 times the same structure. Then the structure is said to have a sixfold axis of symmetry or a hexad. So a hexagon or a benzene ring is said to have a sixfold axis of symmetry. If similar appearance of a crystal occurs when we rotate through an angle of 360 by n, then the axis is called an n-fold rotational axis, and it is said to have an n-fold axis of symmetry. Now let's look at the types of rotational symmetry axis which are possible in crystals. The first is the one-fold rotation axis. Right? Let's imagine a structure. Look at this structure. If I want this identical structure after rotation, there is no possible angle of rotation in which I can get this identical structure back. So in fact, I will have to rotate it complete 360 degree if I want to get this structure. Please understand the imaginary axis that you are thinking of is the one which is perpendicular to the plane or the perpendicular to the structure that you are seeing. That is, imagine it to be moving towards you, coming out of the screen, or if you are drawing it on a paper, then perpendicular to the plane of the paper. Now, if I were to rotate it, so let's say this is the plane of the paper and this structure is drawn. I will have to give it a complete 360-degree rotation for me to get an identical structure. There is no any other angle at which if I give the rotation, I will get this structure. So this structure, because it repeats itself only one time every 360 degree, it is said to have a one-fold axis of rotational symmetry. Now let's look at the twofold rotational axis. Now what is a twofold rotation axis or twofold rotational axis? If I get an identical structure after a rotation of 180 degree, that is twice in a 360-degree rotation, then it is said to have a twofold rotation axis. Please see these examples. In all these three examples, please imagine there is an imaginary line which is either extending towards you from the screen that you are watching or is perpendicular to the page or the blackboard. Now, if I were to rotate this by an angle of 180, then only I will be able to get an identical structure. Another 180, I will get an identical structure. So in a 360-degree rotation, I am getting this structure twice. So it is said to have a twofold rotation symmetry. Similarly, in this structure, if you imagine that there is a rotation around an imaginary line which is passing through the crystal, and after an 180-degree angle, it gives a similar appearance, then it is said to have a rotational symmetry of twofold. Similarly, in this structure. Now let's take a look at the threefold rotational axis. If I were getting a same structure, same identical structure for rotation around an imaginary line passing through the structure after every 120-degree or thrice in a 360-degree complete rotation, then it is said to have a threefold axis of rotation or threefold rotational axis. So this triangle, a filled triangle, is used to symbolize the location of threefold. So just imagine an imaginary line which is coming towards you from the screen, or if you're drawing it on a plane of the paper, perpendicular to the plane of the paper, and you give it a rotation. After 120, you get the identical structure. Another 120 meters, 240, you get an identical structure. Another 120, you get an identical structure. Similarly, this structure, you get a threefold rotational axis of symmetry. Now, let's take a look at the fourfold rotation axis. Now, fourfold rotational axis of symmetry or fourfold rotation axis is a, a symmetry element in which, if you imagine an imaginary line which is passing through the center of the crystal, then you get the same identical structure after every 90-degree rotation or 4 times in a 360-degree rotation. So imagine this to be, this is a square or a filled square, and you imagine so let us imagine that there is a square, and in the square you have a imaginary line which is passing through the center, and you give it a 90-degree rotation, you get an identical structure. Another 90, identical structure. Another 90, identical structure. Another 90. So 4 times in a 360-degree rotation you are getting this. So then it is said to have a fourfold axis of rotational symmetry. Similarly, this structure also has a fourfold rotational axis of symmetry. In case you are not able to visualize this, the best way to do it is, initially you will find it a little difficult because in the it's a lot more to do with how you look at the picture, but once you get the hang of it you will understand. So how do you do it? You first draw it on a plane of paper, then look at the structure and see whether there is an imaginary axis which is passing through the center, and when you give it a rotation, do you get the identical structure? If you are not able to figure it on your own, you can label one of the corners. Then you will understand that whether the rotation has taken place and whether you're getting an identical structure or not. Similarly, let's take a look at the sixfold rotation axis of symmetry. If you rotate a structure and after every 60-degree you get a identical structure, then it is said to have a sixfold rotation axis. Or in a 360-degree rotation, you get 6 times the identical structure. Please understand that you're imagining that the imaginary line is passing through the crystal and you are giving it a rotation of 60-degree. You get a similar appearance. So what is the rotation axis? Sixfold rotation axis. I have already said that it is 360-degree by n. So 360 by 60, you get sixfold rotation axis. So just see, this is a regular hexagon. Just imagine this is a hexagon and you give it a 60-degree rotation. So this will move here, this will move here, this will move here. And when you look at it, this is identical structure. So you wouldn't know. So it is identical for every 60-degree rotation. Similarly, this structure is also having a sixfold rotational axis of symmetry, and you are able to figure it out. Just take a look at the picture, have a feel for the axis, and you will be good to go. Now, let us look at the rotational axis of symmetry which are present in a cube. Now, I did tell you that there are 7 Bravais lattices. We are majorly interested in cube because they're simple and more easy to visualize for our course. So we are doing only cube. Now, just see what are the various kinds of rotation axes of symmetry that are there in a cube. So the first is that there is a fourfold rotational axis of symmetry, and you can see these are the one which are passing through the, so you have an imaginary line, just imagine an imaginary line which is passing through the center of 2 opposite faces of a cube. So just see, so there are how many faces? 6 faces. So how many pairs of opposite? 3. So you have 3 of these and they are having 4 rotational fourfold rotational axis of symmetry. Now let's look at the ones which are passing through the body diagonal. So just imagine, so top front corner and the bottom or opposite corner. These are the body diagonals. Huh? So through the body diagonals, you are getting rotational axis of symmetry, and therefore you have these are threefold rotational axis of symmetry. Then there are ones which are between the edges. So how many edges are there? There are 12 edges. So six pairs are there. So the center of two opposite pairs of edges. So this is just the top and this is the bottom. So you have these are twofold rotational axes of symmetry. So these are the kind of rotational axes of symmetry that are there in a cubical structure. So how many of these are there? 13. There are fourfold axes of symmetry, there are threefold axes of symmetry, there are twofold axes of symmetry. Now let's look at the plane of symmetry, or the which is called as the mirror symmetry. So what is a plane of symmetry? A plane of symmetry is an imaginary plane on a crystal system. With respect to the plane, the crystal is divided into two halves. One half is the mirror image of the other half. Now, I'm explaining to it. So, if you imagine this is a cube, and you imagine there is an imaginary plane, let's say a paper is passing through the crystal, and the two halves through which, through two halves, are looking like the mirror image across the plane. That is called as a plane of symmetry. I'm repeating, what is it? It's an imaginary plane in a crystal system. With respect to this plane, the crystal is divided into two equal halves, and the one half is a mirror image of the other half. So just imagine this is a cube and there is a paper passing through it. A cube, paper passing through it. The one half is a mirror image of the other half. So this is what is called as plane of symmetry, and a crystal can have number of planes of symmetry. So remember, what is a plane of symmetry? It's a plane. Just imagine a paper, if it is placed in the crystal in such a way that the crystal gets divided into two equal halves which are mirror image of each other, then it's all called as a plane of symmetry. Now just look at this structure. So this structure, if this is the plane, let's say this is a structure and there is a plane. So this half is a mirror image of this half. So this is called as a symmetrical structure. And now look at this figure. You put a plane. Imagine a paper being kept. This is not a mirror image of this. So this is not having a plane of symmetry. So any two-dimensional surface that when passed through the center of a crystal divides it into two symmetrical parts, then it is said to have a plane of symmetry, or a mirror image is being formed. So in the so look at these structures. Just imagine this is a rectangle. You put a plane. This half is a mirror image of this half. Similarly here, this half is a mirror image of. So what is the difference between the four structures? There is some difference. You see there is solid line in these two structures and there is dotted line. This is because there are two kinds of planes of symmetry in the crystal structures. One is a rectangular plane of symmetry, the other is a diagonal plane of symmetry. So a rectangular plane of symmetry is an imaginary plane passing through the midpoints of two opposite faces of a crystal, and with respect to this plane, the crystal is divided into two halves. So it's an imaginary plane which is passing through the midpoints of two opposite faces of a crystal, and with respect to which the crystal is divided into two halves. One half is a mirror image of the other half. Here also one half is a mirror image of the other half. Then there is a diagonal plane of symmetry. It is a plane of symmetry passing through the diagonal of two opposite faces of a crystal. So just imagine one is a top, the other is a bottom. That's why it is a dotted line. So it's an imaginary plane passing through the diagonal of two opposite faces of a crystal. And with respect to this, the crystal is divided into two halves. One half is a mirror image of the other half. One half is a mirror image of the other half. Right? So if I see this, the rectangular on the left has a mirror plane that runs vertically on the page and is perpendicular to the page. So if you draw this rectangle on a page, then imagine there is a paper which is able to cut through that paper. Then this is a rectangular, right? Similarly, the dash parts of the rectangle here show that the parts of rectangle would be seen as a reflection in the mirror, right? Uh, so this has to be understood. This rectangle on the right has a mirror plane that runs horizontally and is perpendicular to the page. So this is perpendicular to the page. So with this, you get a feel of the rectangular planes of the symmetry and the diagonal planes of symmetry. Now let's look at them in terms of cubic system. In a cube, there are 9 planes of symmetry. There are 3 rectangular planes of symmetry and there are 6 diagonal planes of symmetry. So this is a rectangular, just a cube cuts into half. Then these two faces cuts into half. Then this two cuts into half. Then the diagonal, just see, it's running from here to here. It's running from here to here and top to bottom. So two opposite edges. Now, how many edges are there? There are 12 edges. So, such kind of diagonal plane of symmetry can be 6 for each two opposite edges. So, you have 6 diagonal planes of symmetry and 3 rectangular planes of symmetry, which are for the two opposite faces. And how many faces are there? 6 faces are there. So, how many pairs are there? 3 pairs are there. So 3 rectangular planes of symmetry. So total 9 planes of symmetry are there for the crystal in a cubic system. Right? Now let's look at the center of symmetry. So what is a center of symmetry? Center of symmetry is a point in the crystal such that any imaginary line passing through this point meet the opposite faces of the crystal at equal distances on either side. A crystal cannot have more than one center of symmetry. Now, a crystal can have multiple rotational axes of symmetry. A crystal can have multiple planes of symmetry, but there will be only one center of symmetry. This center of symmetry is also called the center of inversion because the crystal structure remains unchanged when the crystal is inverted through this center of symmetry. In other words, it is the point in the crystal with respect to this point if a line is drawn in opposite direction. So this is the center, let us say a line is drawn in opposite direction, then it will intersect the surface of the crystal at equal distances in both the directions. So this is center of symmetry. Now just see, this is the cube and this is the center of symmetry. So if a line is drawn in opposite direction, in any opposite direction, then so here if I go and then I go this side, I will meet the surface of the crystal at equal distances. Similarly, if I go this side, then at the same equal distance on the other side, I will meet the surface of the crystal. So this is like that. So it is also called a center of inversion. Like I said, the crystal structure will remain unchanged if I invert it through this center of symmetry. Now, just let's take a look at these structures. These structures help us understand what is center of symmetry or the center of inversion. Now, most crystals will have a center of symmetry, even though they may not possess either plane of symmetry or axis of symmetry. So, if you can imagine an imaginary line from the surface of crystal facing through the center of the crystal and it intersects a similar point at equal distances from the center, then the crystal has a center of symmetry. So just see, this is the center of symmetry. This is you go this way at equal distance and you go this way, you meet identical things. You go this way, you go this way. You meet identical things. You may go here, you go here. You meet. So this is the center of symmetry or center of inversion. You must understand that in this operation, lines are drawn from all points on the object through a point in the center of the object. So if I draw a line through the center of the object, then I am performing the symmetry operation. So see, this is the center. I draw a line here. I draw a line here at equal distance, and I meet exactly same points on either side. The lines will have lengths which are equidistant from the original point. And when the ends of the line are connected, the original object will be reproduced inverted from its original appearance. So just see, if I mean any which way you see these structures, any which way you see, you will get identical structure. So here you've got identical, here you've got identical, and that has happened because you have inverted the structure through this center of symmetry. Let's take a look at the roto-inversion or rotational inversional symmetry. So what is roto-inversion? When you combine rotation with a center of symmetry operation, then this is called as rotational inversion. Objects that have roto-inversion symmetry have an element of symmetry called a roto-inversion axis. That is, you are rotating the object and then performing a symmetry operation involving the inversion through the center of symmetry. Now, let's take a look at the twofold roto-inversion, threefold roto-inversion, fourfold roto-inversion, and sixfold roto-inversion. So the roto-inversion is very much similar to the rotational axis of symmetry. In fact, it is also called as improper axis of symmetry because here also there is an imaginary line around which the rotation of the object has to take place. So in the twofold roto-inversion, you rotate the object by an angle of 180 degree, and this is followed by inverting it through an inversion center. A twofold roto-inversion axis is symbolized as bar 2. Similarly, you will have a threefold roto-inversion which involves rotating the object by an angle of 120 and then inverting through a center. The threefold roto-inversion axis is denoted as bar 3. A fourfold roto-inversion will involve rotating the object by an angle of 90 and then inverting through a center. And the axis is symbolized as bar 4. Similarly, you will have a sixfold roto-inversion which will involve rotating the object by 60 degree around the sixfold roto-inversion axis and then inverting it through the center. And this is represented as bar 6. Now, let's look at the summary of what we have studied about the cubical crystal. So we've said that there is center of symmetry in a cubical crystal, there is axis of symmetry in the cubical crystal, and there are planes of symmetry in the cubical crystal. How many centers of symmetry are possible? Only one, so one. How many axes of symmetry were there? There were 13, which were 3 fourfold axes of symmetry, 4 threefold axes of symmetry, 6 twofold axes of symmetry. You also had planes of symmetry. So there were 3 rectangular planes of symmetry and 6 diagonal planes of symmetry. So all in all, you had 23 symmetry elements in a cubical crystal. We can also take a look at the tetragonal system. So here we have taken an example of a tetragonal system to show how the various symmetry elements are combined in a somewhat completed crystal. Here the crystal has the following symmetry elements. It has a fourfold rotation axis. It has twofold rotation axis, but how many? 4. It has 4 twofold rotation axis, 2 cutting across the faces and 2 cutting the edges. There are also mirror planes. How many mirror planes are there? 5 mirror planes are there. 2 cutting across the faces, 2 cutting through the edges, and 1 cutting horizontally through the center. There is also a center of inversion. In this way, we can find out the symmetry elements and the symmetry operations which are present in any crystal. Now, let's talk about certain terms which are needed to describe the geometry of a crystal. These terms are called as crystallographic terms. The first is the crystallographic axis. Now, in order to describe the complete structure of a crystal, that means planes which are present in the crystal, the relative direction, and the orientation of the faces, 3 non-coplanar coordinate axes called the crystallographic axis are chosen arbitrarily which meet at a point. Now, choice of these axes can be done in a number of ways, but the best choice is usually the lines either coinciding with or parallel to the edges between the principal faces. These axes are represented as x, y, and z, and the angle between the axes opposite to the intercepts are represented by alpha, beta, and gamma respectively. Now let's talk about standard or unit plane. Now generally any face of the crystal will cut one or more of the 3 crystallographic axes. The face which will cut all the 3 axes is known as standard plane or a unit plane. The distance of the points of the intersects of the 3 axes from the origin are called as intercepts. The intercepts A, B and C on X, Y and Z axis are generally called the crystal parameters. Now how do we measure them? So you have an origin, the face will cut the axis. When it cuts at the X axis, that is measured as A. When it cuts on the Y axis, it is measured as B. When it cuts on the Z axis, it is measured as C. Now let's talk about axial ratio. So the ratio of intercepts made by a unit plane on the crystallographic axis is called as the axial ratio and is represented as A is to B is to C or A upon B is to 1 is to C by B. So you see this is a face. It's cutting on the x-axis at point A. The intercept is small a. It's cutting on the y-axis and the intercept is called as B. It is cutting on the z-axis and the intercept is called as C. Now you see this is a plane which is cutting all the 3 axes and the ratio A is to B is to C, the ratio between the intercepts is called as the axial ratio. Let's talk about the laws of crystallography. There are 3 basic laws of crystallography regarding the forms of the crystals. The first is the Steno's law of constancy of interfacial angles. Second is the law of constancy of symmetry. Third is the Wheeze law of rational indices or intercepts. Now what is Steno's law of constancy of interfacial angles? This is also called as the first law of crystallography. The size and shape of the crystals of one and the same substance may vary with the conditions under which the crystallization occurs. In spite of the different sizes and shapes of the crystals of the same substance, the interfacial angles between the corresponding faces remains constant. This is called the law of constancy of interfacial angles and was first realized by N. Steno in 1666 for quartz crystal. The measurement of the interfacial angles in crystals is therefore important in the study of crystals. The interfacial angles may change with the change in temperature of the crystals. The instruments which is used for the measurement of interfacial angles is called as goniometer. The angle between the corresponding faces of various crystals of the same substance are constant is the main crux of this law. This law states that the angle between the adjacent corresponding faces is interfacial angles of the crystal, and this is always constant in spite of the different sizes, shapes, and mode of growth of the crystal. Now, let's talk about the law of constancy of symmetry. This law states that all crystals of a particular substance have the same elements of symmetry, that is, plane of symmetry, axis of symmetry, and center of symmetry. Now we know that the total number of planes, axes, and center of symmetries which are possessed by a crystal is called as the elements of symmetry. And the total number of elements of symmetry in a cubic crystal is equal to 23, where the plane of symmetry is 9, axis of symmetry is 13, and center of symmetry is 1. Now let's talk about law of rational indices or intercept, which is given by R.J. Wheeze. Now this law states that the ratio of intercepts of different faces of a crystal with the three axes are constant and can be expressed by rational numbers, that the intercepts of any face of the crystal along the crystallographic axis are either equal to the unit intercepts made by a unit cell, A, B, and C, or simple small whole number multiples of them like L, M, N, or it can be restated as intercepts made by any face of the crystal on the crystallographic axis are either same as those of the unit plane, that is A, B, and C, or some simple whole number multiples of them like LA, MB, and C, where L, M, and N are simple whole numbers. Or third, one or two intercepts may be infinity if the face is parallel to one or two axes. Now let's talk about the Wheeze indices and the Miller indices. So what are Wheeze and Miller indices? These are a set of integers which are used to describe a given plane in a crystal. Let's first talk about the Wheeze indices. The intercepts of unit plane, I'm repeating, what is a unit plane? A plane which cuts x, y, and z axis all three. So the intercepts of the unit plane on x, y, and z axis, that is crystal parameters, are A, B, and C respectively. Now if a face parallel to the unit plane cuts the three axes with intercepts x, y, and z respectively, then according to the law of rational indices, x is equal to LA, y is equal to MB, and z is equal to NC. The coefficients or multiples L, M, and N are called as the Wheeze indices of a plane. The corresponding plane is described as LMN plane. These are generally small whole numbers, but this is not always true. There may be fractions of whole numbers as well as infinity when you express a plane. I'm repeating, you have a unit plane which cuts x, y, and z axis. The intercepts are A, B, and C respectively. Now, if that is true, then your x, the intercept, can be written as x is equal to LA, y is equal to MB, and z is equal to NC, where L, M, and N are the Wheeze indices. These are small whole numbers which are used to express a plane. Now let's talk about the Miller's indices. The Miller indices was given by W. H. Miller. Miller indices are a symbolic vector representation for the orientation of an atomic plane in a crystal lattice and are defined as the reciprocal of the fractional intercepts which the plane makes with the crystallographic axis. What were the intercepts which the plane was making with the crystallographic axis? They were nothing but the Wheeze indices. So the Miller indices of a face are the reciprocal of the Wheeze indices, which have been expressed as integers. In general, when Miller indices are denoted by H, K and L, then the plane is represented by H, K, L within the brackets. Miller indices of a crystal are in general small integers as well as zero. Please understand they are a shorthand notation which are used to describe certain crystallographic directions and planes in a material. You can use brackets, square brackets. You can use just lower uh, lower than sign and a greater than size to enclose the numbers. You can use a small bracket like this, parenthesis, to enclose the number. These do not define merely a particular plane, but a set of parallel plane. It is only the ratio of Miller indices which is of importance. That is, let's say this is a 422 plane. Now 422 plane is same as a 211 plane. Similarly, 200 plane is the same as the 100 plane, and so on. Now, how do we find Miller indices and Wheeze indices? Very simple. The procedure is as follows. You have to prepare a 3-column table with the unit cell axis at the top of the columns. In each column, the intercept, which is expressed as a multiple of A, B, or C of the planes with the axis, that is Wheeze indices, is written. You invert all the numbers, you take a reciprocal of them, you clear the fractions to obtain H, K and L. I'm repeating, how do you find out the Miller indices? You prepare a 3-column table with the unit cell axis at the top of the columns. In each column, the intercept, the multiple 3A, 3B, 2C, this is written. This is nothing but a Wheeze indices. Now you take a reciprocal of these numbers, that is the Wheeze indices. You clear the fractions to obtain H, K, L, and hence you will get the Miller indices. So the example here taken is of 3A, 3B, 2C. Now the Wheeze indices are what? 3, 3, 2. You take the reciprocal, you get 1 by 3, 1 by 3, 1 by 2. Now you have to clear the fractions, so you take a LCM and you multiply each by the LCM. So 1 by 3 into 6 you get 2. 2 and 1 by 2 into 6 you get 3. So you get Miller indices as 2, 2, 3. Let's take a look at certain examples on how to calculate the Miller indices of crystal planes. The first example is of a plane which makes an intercept of 2A on the x-axis, 3B on the y-axis and C on the z-axis. We've already talked about how to do that. Let's make 3 columns with the intercepts A, B, C. The intercept on the x-axis was 2, y-axis was 3 and on the z-axis is 1. So 2, 3, 1 and these are called as Wheeze indices. You take a reciprocal of them 1 by 2, 1 by 3, 1. You convert them into clear numbers. So you take an LCM, multiply with the LCM and you get 1 by 2 into 6. So you get 3. 1 by 3 into 6 you get 2 and 6 into 1 you get 6. So the Miller indices of this plane are 3, 2, 6. Let's take another example. In the other example, the intercept made are A by 2, B, 3C by 4. Look at this figure. This is the plane. It makes an intercept of A by 2 on the x-axis, B on the y-axis, and 3 by 4 C on the z-axis. Now these are the intercepts. So 1 by 2, 1 and 3 by 4 are the intercepts. You take a reciprocal of them and you get 1 upon 1 by 2, 1 upon 1 and 1 upon 3 by 4. When you take them, you get and you convert them into clear numbers or clear fractions, you get 6, 3, 4. Hence Miller indices are 6, 3, 4. Similarly, look at this plane. Now just see this plane makes an intercept of A on the x-axis, B on the y-axis, and it is parallel to the z-axis. So what will be the intercepts? 1, 1 and infinity. You take a reciprocal, so 1 upon 1, 1 upon 1 and 1 upon infinity, and you get 1, 1, 0. So the Miller indices of a plane which cuts two axes and is parallel to one of the axes will be in the form of two ones and 1, 0. In this case, because this was parallel to z axis, so 0 has come at the z position. Now look at this plane. Now this plane is also cutting only the x-axis. It is parallel to the y-axis and is also parallel to the z-axis. So the intercepts are 1 by 2, infinity, infinity. Again you take a reciprocal. In this case, when you take a reciprocal, you get already clear numbers 2, 0, 0. So Miller indices are 2, 0, 0 for this plane. Now similarly, very simple A, B, C. You have 1, 1, 1 for the three axis. You take a reciprocal, you get the same as Miller indices. Very simple, right? Now let's look at this example. 6A, 3B, 3C. You write down the numbers for the intercepts, that is the Wheeze indices. You take a reciprocal 1 by 6, 1 by 3, 1 by 3. You make them into clear number. So you get 1, 2, 2 and you get Miller indices as 1, 2, 2. Now look at this example. This is different slightly. The intercepts are 2A on the x-axis, minus 3B on the y-axis, minus 3C on the z-axis. Again, you follow the same example. You write the Wheeze indices 2, minus 3, minus 3. You take a reciprocal. Get 1 by 2, minus 1 by 3, minus 1 by 3. You convert them into integers. How? You take an LCM. You get 3, minus 2, minus 2. Now you do not write minus 2 and minus 2 as this. You write 3, 2 bar, 2 bar. So the minus is written as a 2 with a bar over it. So Miller indices are 3, 2 bar, 2 bar. Now like this example, very similar to what we have already done. The intercept on the x is minus a, intercept on the y is minus b, and the z it is parallel to. So infinity. So minus 1, infinity. You take a reciprocal, you get minus 1, and 0. Now you do not write minus 1 as minus 1, you write it as 1 bar. So 1 bar for y-axis and 0 for the z. So 1 bar, 0 is the plane. Similarly this a by 2, b by 4, infinity. You write down the Wheeze indices 1 by 2, 1 by 4, infinity. You take a reciprocal, you get 2, 4 and 0. And because it is already a clear number, so you get 2, 4, 0. Now let's look at this plane. The intercepts are 1 by 2, 1 by 4 and infinity. You take reciprocal, you get 2, 4, 0. So the plane is indexed as 2, 4, 0 plane. Now look at this plane. This plane has made an intercept of 1 by 2 on the x-axis, parallel to the y-axis, parallel to the z-axis. So 1 by 2, infinity, infinity are the intercepts. You take a reciprocal, you get 2, 0, 0. So the plane is indexed as 2, 0, 0 plane. Another one, 2A, 3B, 4C, A, B, C. The intercepts are 2, 3, 4. You take a reciprocal, 1 by 2, 1 by 3, 1 by 4. You get the Miller indices as 6, 4, 3. Why? Because the LCM of 2, 3, 4 is what? 12. So when you make them into clear numbers, you get 6, 4, 3, and the plane is indexed as 6, 4, 3 plane. Now let's take a look at the planes that we've been talking about just to get a good idea of it. Look at this. This is a 1, 0, 0 plane. The 1, 0, 0 plane will cut the x-axis at the 1 and will be parallel to the y and the z. Look at this plane. This cuts x-axis, this cuts y-axis, but is parallel to the z. So it is a 1, 1, 0 plane. Look at this plane. It cuts x, y, and z. So this is a 1, 1, 1 plane. So this is how you can very easily figure out. Look at this. This is a 0, 0, 1 plane because look at this. It is at a distance of 1 from the origin for the z-axis, but it is parallel to the x and y. We already know about the 1, 0, 0. So it is cutting x, but is parallel to y and z. Look at the 0, 1, 0. It is parallel to the x, it is parallel to the z, and it is cutting y. So it is a 0, 1, 0 plane. So with this, you have an idea of what kind of planes are there. Now today, what have we done? We've talked about the external features of a crystal. We've taken a look at the elements of symmetry in the crystals. We've talked about axis of symmetry, plane of symmetry, center of symmetry. We've also talked about the rotation inversion symmetry, which is also called as roto inversion. We have taken a look at the crystallographic terms which are there in defining a crystal. We've talked about the laws of symmetry, the 3 laws of symmetry, and we have learned about how to calculate the Wheeze indices and the Miller indices. So with this, we finished today's lecture. Thank you so much for your patient hearing. This is the end of the lecture. Please take care of your parents, yourself, and your family members. All our best regards with you.